Today we're going to do 7.2, which is volume, and we're going to actually start talking about volume of three-dimensional objects. We have in the past done area, right? Area underneath the curve, and we've done area underneath the curve using Riemann sums. So we take a bunch of rectangles and we find their areas and we add them all together. And then we've got more complicated into the calculus part and we've integrated, right? Or what you're doing when you're integrating is you're finding the area underneath the curve using an infinite amount of rectangles, so giving you an exact area underneath the curve. Today what we're going to do with integrals is we're going to actually find the volume of three-dimensional solids. We're going to find the volume of three-dimensional solids using the method called the disk method. We're going to find volume of solids like the shapes that you see right here, maybe like a little bottle, a root beer bottle, or a funnel, or a pill, something like that, where these solids are called solids of revolution, where you can take a line and kind of revolve it around that line and you come up with that shape. Those shapes are called solids of revolution. So if a region in a plane is revolved about a line, the resulting solid is called a solid of revolution. The line that you rotated around is called the axis of revolution. And so we're going to find the volume of these solids of revolution by using rectangles still. But in this case, when I take this rectangle and I revolve it around this axis of revolution, this line, I'm going to end up not getting a rectangle anymore. I'm going to get more like a disc, okay, or a cylinder. And so if you recall back again when we found the area underneath the curve using a whole bunch of rectangles, we integrated the area of those rectangles. So my bases times my heights, where the height of each rectangle was the function f of x, and the base of each rectangle was my delta x, my change in x, or when we integrate it, we use dx, right? And so when we integrate it, we can integrate it from a certain value, from a to b, and find the exact area underneath the curve. Well, when I do a three-dimensional solid, if I'm doing a solid of revolution, that function now turns into a three-dimensional shape, or like we just said before, a cylinder, where the volume, or excuse me, where the volume of the cylinder is pi r squared h, where you have your radius and then you have your height. Well, in this case, they call the height w for whatever reason, or the width, I guess, of your disk. Well, in order to find the exact volume of your solid, we can integrate it, okay, using the disk method. So we're going to integrate. We have our pi is just a number that I can bring out front. And we're going to integrate our radius squared. Well, in this case, our radius is really going to be our function, our f of x. So we're going to take our function and square it. And then we're going to do all of our little widths or our heights or our dx's. And then we can integrate it from a to b, our limits of integration. A lot of times they use capital R for f of x, so they call it more of like a radius instead of a function. Okay? And that's when you're revolving it around a horizontal axis of revolution. But sometimes we end up revolving around a vertical axis of revolution. So if you kind of turn your head sideways, you're still going to integrate it, still using a disk, so pi r squared. But in this case, instead of using with respect to x, we're going to integrate it with respect to y. So all your variables change to y's, and then your limits of integration are from c to d on the y-axis, not the x-axis anymore. Okay? Okay, so let's do an example here. I have this example where we're asked to find the volume of a solid by revolving it around the region bounded by the graph of f of x. If f of x is the square root of sine x, we want to do the in between that and the x-axis from 0 to pi about the x-axis. So that means we're taking the function, the square root of sine of x, and we're taking the x-axis and we're revolving it around the x-axis. So we're revolving it around itself. If we end up revolving it around itself, it's going to end up flipping on top of itself and rotating around and ending up looking like this little egg shape here, or kind of like the shape of Kyle's head. So let's find let's find the volume of this solid of revolution. We're finding it again from 0 to pi, because that's what it says in the problem, around the x-axis. So here we go. So we're going to use our disk method, because they're little rectangles. If we revolve them around, are going to end up looking like little cylinders or disks. So here we go. We have our pi r squared h, h being our widths of our little disks, and we're integrating it from 0 to pi on the x-axis. We're going from 0 to pi. We've got to figure out then what our radius is. So from the center up to my little egg, or from the center up to my little egg here, or from the center up to my little egg. No matter where I am on that little egg, it corresponds to the function, or the square root of sine of x. Make sure you square it, because that's the radius squared, and then you have your dx there. The square and the square root cancel, and I'm left with just the integral from 0 to pi of sine of x, and then we can integrate sine of x. We have pi times negative cosine, so negative pi cosine x from 0 to pi. So now let's evaluate it, plugging in our pi and our 0. All right, cosine of pi is -1 minus cosine of 0, which is 1. If I combine my like terms here, I got a negative pi times -2. Two negatives make a positive 2 pi. So that means the volume of Kyle's head is 2 pi. Maybe it's an empty volume, but it ends up being about 2 pi. All right, so what happens if we start revolving something around an axis that's not the x-axis? Okay, so if we're revolving, we're not always revolving around the x-axis. Sometimes we're revolving around some type of other line or axis of symmetry. So let's do an example that looks like that. So we have this function, 2 minus x squared. And an x squared graph is going to be a parabola, right? A parabola opening down up at 2. We want to use that equation and the equation g of x equal to 1. So y equals 1 is a horizontal line up at y. And we want to revolve it around the line y equals 1. So we're actually revolving it around itself. So if I were to take that little piece of the parabola, rotate it around itself, I end up getting the shape of, oh look, Will's head. So let's find the volume of Will's head. Here we go. We've got to first figure out where we're integrating it from. We need our limits of integration. In the last problem, it gave it to us. In this problem, it doesn't. So that's one thing that we have to find. We have to find the limits of integration. Okay. We're still going to use our disk method, because when we revolve around, we're using little rectangular disks that are going to be rotated. So they're going to end up looking like little cylinders. So we have our pi r squared h. Again, we need to find our limits of integration, and we also need to find our radius. We need to figure out what the radius of Will's head is. So here we go. Let's find limits. We're finding the limit, and what we're really doing is finding the intersection of those two functions, right? We have that horizontal line, y equals 1, and we have the parabola, the 2 minus x squared, and we want to find where they intersect. So can I do a system of equations and set them equal to each other? That will help me find my x's, where they intersect, and so those will be my limits of integration, where they intersect, so I can find the volume in between. I end up getting x equals plus or minus 1, which you can see in the picture, but remember they're not always going to give you a picture, so that's why we needed to find them. The other thing that we need to find is the radius of my solid of revolution. So I need to go from my center to my outside. If I'm going from the center to my outside, my center isn't my x-axis, remember. Remember, I've moved up a little bit. So if I want to find my radius, I need to find the little distance in between. I need to find the distance from the top of my shape to the center of my shape, which really the center is what? Isn't it y equals 1, and I'm revolving around that? So I need to find the stuff in between. So can I do top minus bottom? Right? Kind of like the area in between two curves. I want to figure out where it goes from the center up to the top. Okay, so top minus bottom functions. My top function being my 2 minus x squared, minus my bottom function being my y equals 1, right? So if I combine my like terms, my radius of my solid ends up being negative x squared plus 1. Okay, so now let's go ahead and use my disk method to integrate. We have pi, we have my limits of integration from -1 to 1. We have my radius squared, don't forget about the squared part, radius squared times my little heights, my little widths of my cylinder or my disk. What I'm going to do before I integrate is actually FOIL this just to make it a little bit easier so I don't have to do any sort of u substitutions. I get an x to the fourth minus 2x squared plus 1 dx. So I'm going to integrate it leaving my pi out in front. We can distribute that later. The integral of x to the fourth is x to the fifth over 5. I have minus 2x cubed over 3 plus x, and we're integrating it from -1 to 1. Plugging in my 1 and my -1, I have 1/5 minus 2/3 plus 1 minus -1/5. That's going to give me a negative and a negative, so a positive 2/3 minus 1. So here we have to find a common denominator. I'll let you guys do that, but we can find a common denominator in this first little section of 15. Combine my like terms, you should end up getting 8 over 15. Don't forget about your pi in front. Find your common denominator in your second set. You should end up getting a -8/15. So those two negatives end up making a positive, and then when you combine like terms, you should end up getting 16 pi over 15. That is the area of the solid, or Will's head. Okay, that's the disk method. Let's do another method called washer method.